6.3, the hyperbola curves. We talked about the hyperbola curves repel each other. The way we're going to notice those whenever we're looking through all the graphs put together, we're going to notice that you've got an x squared and a y squared, but they have different signs, either x squared minus y squared or y squared minus x squared. The signs will be different. And that helps my brain, what helps my brain I should say, is the minus makes the curves repel. Either sideways repelling or an up and down curve. We talked about the power plant, that tower has the shape of hyperbola curves curved inward that follows this mathematical definition of a hyperbola. Okay, so this is the standard form equation. What our goal is to make our equation look like if we want to be able to graph it. Where x squared is over something squared, just like the ellipse. This thing is almost the same set of steps, except we have minus y squared over something squared, and again we want to make these equal 1. The reason we have to do this for the ellipse and the hyperbola is the coefficients may be different. On the ellipse, the coefficients were definitely different. If the coefficients were the same, it would have made a circle, and that we have a little different way of working around our circle. But anyway, because the coefficients may be different on the hyperbola as well, we can't just eliminate the coefficient to complete the square, so we have to approach it from a different side. So anyway, our approach for the ellipse and the hyperbola is to make it equal to 1. So you'll notice the same deal. All right, if it is an x squared minus y squared, it will be a sideways hyperbola or a horizontal hyperbola. If it is y squared over something minus x squared over something, if the y squared is positive minus x squared, it will be a vertical hyperbola, up and down curves. So just another thing to memorize, right? You have a note on that. Okay, so for example, here's how we get our curves graph. And notice this does not have an offset from the centering. You know how on the last example we talked about we had plus and minus on the x? We may have another one of those in an example, but if there's nothing added or subtracted, then you don't have to shift it from the origin. It's centered right at 0, 0. And then we take the square root of what's under the x squared, so that represents something squared, so again we square root it. It's 4, so we go 4 on the x-axis, and just so happens this one has the same coefficient, it's 4 again. So we're going up and down by 4s. If this were a plus sign, just like we did earlier, I would circle it together. But because it's minus, that means my curves are repelling one another. To get that exact curvature in there, we can make a box. It's not part of the graph, it's just guidelines. You know how we always dot asymptotes back from chapter 3? So it's kind of a dotted box. Then putting an X through the box will give you the asymptotes for this graph to help you get the exact curvature in there. All right, so this is just fun, right? Just draw all kinds of figures. So box around your points, and then an X through your box, and here are your curves. At your points, if it's sideways, follow your curves. Follow your asymptotes to make your curves fit in there. So that's one side, and then the other side just like it over. And so actually the only thing that's the solution are just these two curves. You kind of got to ignore that step in the middle. That was just our guidelines to graph it. All right, so you know we're always asking about domain and range. So the domain of this graph would be negative infinity because this graph is opening. It would have x values all the way back if we continue the graph. So negative infinity up to and including the point -4. So bracket, it should be touching that. Then union, we skip over all of this x area here has no y coordinate that goes along with it. So there's nothing in here for the x or the domain. So skipping over that, then it picks up again at 4, and the graph goes out to positive infinity there. For the range, now I know it seems like we've skipped some stuff in here and it looks like some of the y values are missing, but don't think that. Just think how low is there a point on this graph. And so there's double lows here. Both of these are going down to infinity and up to infinity. So there's a stretch all the way through the graph from low to high. There's no break in the range. So negative infinity to positive infinity. There are y values without skip overs. All right, so next problem. So I'm thinking this should be a hyperbola again because I have an x squared and a y squared. It doesn't matter if they're different coefficients or not. That's not the deciding factor like on the circle if you have the same coefficients if it was plus. But on the minus, that's all there is to it. If it's an x squared and a minus y squared or a y squared and a minus x squared, I know it's going to be some type of hyperbola. So my goal is to make it equal 1. So divide by 36 to get it in standard form. 9 divided by 36 comes out evenly as 4. 4 divides into 36 as 9, and that equals 1. And then you're ready to roll with it. Now, I've not worked up to the ones where you have to complete the square to find the centering. The 2 examples we just did, there was no issue with that because they were centered at the origin. Remember, if you have a plus or minus attached to that, that means it has an offset of the centering. And the way it looks algebraically, if it's all messed up, times out together, you may have a 9x squared and 2x and a 3y squared and a 4y, a bunch of terms that you have to pull together and complete the square. So we're going to see that in a minute. But this one's clean. There's just an x squared term, just a y squared term, so I don't have any offset or complete the square needs. So I divide out the last term to make it equal 1. Now it's ready to graph, starting at the centering, origin, underneath the x, I square root that, which would be 2, so I'll go out 2. Underneath the y, square root of that is 3, so I'm going up and down by 3s. Right, if it was a plus, I would pull that together and it'd be an ellipse, but because it's a minus, the curves repel one another. So the strategy is to draw a box and an x through your box. And if it's x squared minus y squared, which it is again, I need to do one of the other type, but x squared and a minus y squared, it's a sideways graph. What helps me remember is if x is positive, it opens on the x-axis. X positive on the x-axis. So the curves go out this way. All right, any questions on that? I think on some of your math Excel problems, it's kind of difficult to determine from the scaling. I'm not overly excited about the math Excel options that I have to assign homework because it's kind of hard to decipher their graphs. You may have to use your microscope, or not your microscope, but your magnifying glass, and blow those up and really study the difference in them. And some of them are very close to one another, so it might not be good enough to just kind of know the curves go that way and they're kind of about that y. You might have to get more specific and point plot. That's what I'll say about your homework. You might have to make a t-table and say, okay, on choice A, it looks like the graph is going through the point 5 and up 2, and on graph B, it's over 5 and only up 1. So which one is it? Well, if I plug in x is 5 to the equation, I can equation solve and know exactly where it should be at x is 5. Though it's going to have 2 answers. I'm at -5, sorry. If I'm back here, I'm at -5 where I was pointing. If I plug in -5, I should get 2 answers. So I should get something up here and something down here. But again, if you can't tell the difference in the 2 graphs, that's what you'll have to do. So how would I do that? Let me just demonstrate that quickly. Back to the original equation, or this form. Hey guys, these are the same equations, so it doesn't matter whichever one you like. It should be the same deal. This one just looks neater. I think I'll do it. No, actually, this is probably better because it doesn't have fractions in it. I think I'll go with the original form. So let's say I'm just going to try to find a t-table value by plugging in -5 for x and equation solve that. So let's see, that's 9 times -5 squared is 25 minus 4y squared. And then let's see, 45. Maybe I should have chosen that smaller number. 45 carry the 4. I think I'm okay. Then subtract that, some basic equation solving. 36, I mean my calculator. 36 minus 225, which is negative 189. Then divide out the negative 4. And I have 47.25. Normally we try not to answer as a decimal to be more exact with a fraction, but where I'm just trying to get an idea of the graph, I think a decimal is okay. Okay, then how do you solve that? Y squared equals 47.25. Square root it. And that's why there's two answers. When you take the square root, you get plus and minus. So the square root of 47.25 is approximately 6.87. So then I'll look at the choices and say which graph is back 5 and up almost 7, 6.8, and also back 5 should be down 6.8. So if you have to equation solve, that's how you do it. Also be careful, and I'm sure you're aware of this with some of the graphing problems you've been doing. Sometimes they count by 2s, sometimes it counts by 1s. So you got to watch the calibration of the graph to see how they're counting. All right, so any questions on this?